Chazil?
Can you hear me?
Yes, we can hear you. So good afternoon all. Welcome back to this session 1 of today's technical session. This session is on methodology of remote sensing technology for carbon monitoring and ecology monitoring. And my name is Rajesh Bahadur Thapa. I am a senior remote sensing and geoinformation specialist at ECMOD. I'm also a member secretary of AOGO Regional Center for Capacity Development. So in this session, we have 2 lectures. One is on remote sensing of inland water eutrophication from Professor Kai-san Song, who is working in Northeast Institute of Geography and Agroecology, Chinese Academy of Science. And then we'll have a 5-minute break. After that, we'll have another lectures by Dr. Ram Avatar, Associate Professor from Hokkaido University of Japan on multi-sensor remote sensing techniques for forest biophysical parameters estimation. Now I would like to invite Professor Kai-san Song to deliver his lectures on remote sensing of inland water eutrophication. And please, Kai-san Song, please floor is yours. I can see your slide is already in the screen, and maybe you can start your presentations, and you will have around 30 minutes. So maybe
okay.
When 5 minutes left, I can also call you the time duration. So please start your presentation. Thank you.
Okay, thank you for the introduction, and good afternoon, everyone. Thanks for the invitation from the organizing committee, also National Remote Sensing Center of China, and also Professor Zhou Jiang for the invitation to giving me this opportunity to present something about remote sensing of inland water eutrophication. By the way, I changed the title a little bit. I think this may fit the topic even better, so I changed a little bit. Sorry for that. And this presentation includes 4 parts. First, I'm going to talk something about the background. Inland water plays an important role in many cases. For example, in drinking water supplies, agriculture, irrigation, fishery, and also they provide beautiful scenery spots for leisure time, and also they have some very important ecological functions. For example, they provide animal habitat. However, due to climate change and also human disturbances, inland water eutrophication and the shrinkage due to the farmland encroachment and the urbanization have become a global environmental and ecological issues. Previous study also indicated that eutrophication is a worldwide issue, which is also very serious in China, US, and some countries in Europe as well. So these are just some lakes that have experienced severe harmful algal blooms, like Lake Erie, that's located in the transboundary region between US and Canada, and also lake in China that have experienced very severe harmful algal blooms. So inland water eutrophication can be generally ascribed to non-point agriculture, pollution, sewage water discharge, and effluent water from industrial and also from domestic usage combined with climate change. So once algal bloom happens, it will deplete the oxygen in the water, so that will kill some fish and also some type of algae that release toxins that is very harmful for our health. So that affects aquatic ecosystem and also drinking water supplies. Satellite remote sensing can be used to evaluate and monitor water qualities of inland waters in the past decade. It is effective ways So why it can be used to monitoring water quality? I think there are three types of optically active components in water. That is the algae and the CDAM. We call it the color dissolved organic matter, and also non-algal particles. All these things have absorption and scattering features, which work together to determine water leaving optical signal that can be sensed by satellite remote sensing observation. Thus, we can use optical satellites to derive those components like algae, total suspended matter, and the CDAM. Some parameters such as the turbidity and also like clarity and trophic state index can also be achieved due to their linkage with those optically active components. Sometimes we also can derive total nitrogen and total phosphorus due to its close linkage with like algae or water clarity or suspended matter. Today, my talk mainly focus on TSM and chlorophyll and clarity, which is determined by Secchi depth. Also, we use satellite remote sensing to determine trophic state index. Shortly, we call it TSI, which is determined by chlorophyll A, STD, and total phosphorus. The methodology for TSI can be tracked down from the formula given by Carlson in 1976. That's published with the Journal of Limnology and Oceanography. If someone interested, maybe can check down this literature. As an extreme case, we can also concern about harmful algal blooms, especially for the cyanobacteria blooms. So now let's move on to the methodology part. We collect more than 2,000 samples from about 400 lakes and reservoirs all across China in the field. We measure spectra using the ASD spectrometer and also determine water quality and pH temperature for also like electricity conductivity in the field using YSI multi-parameter instrument. Since 2004, we have conducted more than 100 field surveys across different parts of China. So in the lab, we determine TSM, chlorophyll A, total phosphorus, and total nitrogen fact scanning. Fact scanning, by the way, is a very effective biomarker to be a surrogate for cyanobacteria abundance. So we use both in situ measured spectra and airborne or satellite imagery data for modeling. So we establish models with empirical or some other methods. For example, machine learning program. So we also use different methods to do atmospheric correction. We know that to derive water quality parameters, we need a very accurate way to remove the scattering impact from the air. So we also use GE to map water quality parameters at a large scale. So we also built some method to do atmospheric correction by our own group, and which is mainly done by my colleague, Dr. Liu Ge. So if someone concerns about this method, we can talk about this later on. And also, I can give you the contact by Dr. Liu, so we can ask him for further help. So further now, let's move on the results section. So with the help of inherent and apparent optical properties, we can determine so which are the diagnostic bands that are sensitive to chlorophyll A retrieval. And also we built a genetic algorithm plus a PLS model to improve the modeling accuracy. We use different data sets to evaluate the model performances. The first one is from data set collected in reservoirs from Indiana, USA, and the second one from South Australia, and the third one, this one, from Lake Taipu, and this one from Silvermere Reservoir, which is the drinking water supply for the city where I'm based, that is Changchun. And so due to the complexity of optical properties for inland water, we also try to classify waters into several types or several groups, and we establish models for each type, which can substantially improve model performances. Here, I would like to point out all these results are based on in situ measured spectral data. Also, later on, I will introduce something about using remote sensing, satellite remote sensing data. So during 2017 to 2019, we collected samples from 45 lakes, and eventually about 270 samples matched up with Sentinel-2 MSI image data. We use those linear regression and also machine learning algorithm to derive chlorophyll A. The result indicates that linear regression and the support vector machine and also cat boost algorithm can also be used to retrieve chlorophyll A. However, SVM performed the best in this specific case. Further, we also met up in situ measured chlorophyll A, which collected during 2011 to 2020 with satellite overpasses, especially for Landsat overpasses within 7 days. Thus, we use about 620 samples to train the random forest model, and then we use about 310 independent samples to validate the model performance. For this below figure, we can see that the model performed relatively well. So in order to build a model for mapping water clarity for global inland waters, we also collect SDD data set from different sources, including our own group and also from our colleagues from Nanjing Institute of Geography and Limnology, Chinese Academy of Sciences, and EPA from US, and James Stat, EDI, and WQP. We also try to do the meta-analysis from South Africa and South America and Africa, and try to cover all the lakes from different parts of the world. And altogether, we collect about 5,600 samples that's used to train and evaluate the model. So we built a unified model by selecting the band combination with the highest correlation with SDD and Landsat top of air data. The unified model predicts SDD value very well. So we also try to do and we also try to validate the model performance with some time series data. Those are just some lakes from that have time series measurement. So a model also based on log transformed Landsat red band or band combinations was developed to map TSM of lakes in China, including Tibet and the east of China. These are just the result from East China lakes. It turned out that the red band is very sensitive for TSM retrieval. So on the left of this slide, multiple linear regression was used to determine the relationship between band ratios and the in situ measured TSI to find out some sensitive band combinations. So on the right, likewise, the multiple linear regression was also used to identify significant sensitive structural variables related to TSI. To strengthen the robustness of this machine learning model, we also try to use blue, red, and all green, red ratio, and also the combinations about to improve the model performance. In order to monitoring harmful algal blooms, we did some work in Lake Hulen, which is also a large lake located in northeast China, where I'm located. More accurately and effectively through remote sensing satellite images, adjusted FAI method with automatic identified threshold was developed. So this method can use both Landsat and MODIS data, and also we adjusted the threshold value that can be changed, and which has a very good performance. So we rather use a single threshold. We use varied threshold values. The left figures just show the comparison of AFAI and the FAI between harms and the clear waters, and also the spatial temporal variations of harmful algal blooms in Lake Hulen. Also, with random forest algorithm and the GEE, we use Landsat imagery data to map chlorophyll in lakes with area greater than 1 square meter during 1990 to 2020, with a 5-year interval for all lakes of mainland China, and try to trace the spatial temporal variation of chlorophyll age in lakes in the past 40 years. The results indicate that eutrophication status of lakes were improved, especially lakes in, for example, for lakes in Tibet Plateau in northeast China and East China. Generally, they have a downward trend, but not for lakes in the Yungui Plateau, where eutrophication is still a big problem. So we also use Landsat imagery data to map TSI in Lake Xinkai, which is located in the transboundary region between China and Russia. So we established a model using samples collected in this specific lake, and the result indicated that TSI has increased substantially in the past 40 years. That's a big issue due to the agriculture around this watershed. We also collect some representative lakes to quantify spatial temporal trophic state using the XG boost algorithm. The trophic lake dominated the proportion of investigated lakes in East China, followed by Northeast China and Yungui. So in the case of lakes in Tibet, the eutrophication is not a big issue in this region. So we also try to find out if the COVID pandemic have impact on lake eutrophication. So as we know, many countries implemented various positive strategies to limit the spread of coronavirus, including lockdown and isolation. We use TSI empirical models to map TSI of lakes in eastern China, especially the Hu's line. That's indicated the population, the most populated region is in the east of Hu's line. We found that the TSI empirical model to map TSI of lakes in East China, and seems that the sudden declaration of lockdown is a good implementation to determine to decline anthropogenic activities within lake ecosystem by minimizing the nutrient input. It is interesting that we found that there's no significant improvement of lake eutrophication after the locking down in spring 2020s in comparison with those in spring 2019. As we know that about 90% of Chinese population lives in the eastern part of China. So even we do the locking down, still there are a lot of nutrients in the sediment that will release and will still sustain the algae blooming or algae growth. So there's no significant improvement due to the COVID-19 pandemic. We also use a unified model to map SDD of lakes with surface area greater than 1 hectare. And the mean SDD of lakes across different continents was about 3.88 meter for all the lakes in globally. So in general, lakes with higher SDD generally exhibit larger internal variability in SDD and vice versa. So also in the mid-high latitude, lake also display high water clarity, and the extremely large number of lakes display low water clarity in Africa, in Oceania, etc. So this slide shows the spatial distribution of lake SDD in North American. Lake water clarity tend to be higher in the United States and Canada, but lower in Greenland and also Central America. Water clarity was generally higher in high latitude region, where large and deep lakes generally abounded. So we also map TSM levels in China, in lakes across China. After 2005, the number of lakes in China showing a significant downward trend. The lakes showing a decreasing trend in TSM concentration are mainly concentrated in the high elevation region, for example, for the Tibet region, and the trophic or hyper-eutrophic are mainly distributed in the eastern part of China. We also try to find out the trend of algal blooms in lakes across China. So spatial temporal variation of algal blooms across China in different climatic regions were analyzed. So the lower right is the abbreviation of different indicators. So include normalized area index or duration of algal blooms and the frequency of algal blooms or early day of the breakout of algal blooms. So these are just the trend of algal blooms in different climate regions. And this one for the duration, and for the first day. We studied the spatial temporal change of algal blooms across the world, and out of about 176,000 lakes with area greater than 1 kilo square was detected globally. So we find out about 863 lakes was impacted by algal blooms. So the left figure just shows the global water and the available images and number. So the right number shows the distribution of lakes and reservoirs that have algal bloom occurrence. And the annual change of algal blooms at each lake and were also analyzed by the slope of frequency of algal bloom against the year of observation. That's the upper right one, and for the upper left one, for the upper right one, is the error ratio against the year of observation in of image data that have been detected algal blooms, and also we try to find out the spatial temporal variation of algal blooms at global scale, and try to find out the pattern. Interannual trend or in algal bloom severity across different countries and were also presented in this slide, and we can see that in Asia and the algal bloom generally have a increasing trend, but for American, we can see that before 2000, it's an increasing trend can be detected, but after 2000, generally in a decreasing trend can be traced. So that's maybe due to the nutrient control practice have an impact on the general trend.
5 minutes left.
Okay, I will try best. Overall, these are just some figures from different parts of the world that have experienced algal blooms. These are just some of the factors maybe driving the driving the global water clarity. And we see that larger lakes do usually have a high clarity, and the small one have low water clarity. And this one just shows the driving forces for algal blooms in China. And we try to find out the reason why some lakes have experienced algal bloom while others not. And we found that fertilizer and also agriculture pollution and population can explain more than the climatic factors. So I just ignore this part. The same reason can be attributed to the algal bloom at global scale, and I will just ignore this part. And now let's summarize and also discuss some the reasons why what we should be concerned. This slide shows the difference of top of air reflectance among TM, on that side TM, ETM plus, and OIY. That we can see that the different band, the relationship between different band have different slopes, and also have different R square. So we should concern about these factors for water quality monitoring, and also the sources for TSM, mainly from soil erosion, and also from different from the resource suspension of from the bottom, and maybe also the reason. And briefly, I would like to summarize that the inherent and the apparent optical properties are the base for the derivation of algorithm for water qualities, and the empirical models like the one we developed, and also machine learning, all have the potential to derive water qualities at large scale, even global scale. So machine learning algorithm generally performs better than the simple linear regression model due to more spectral variables was incorporated. That's why, and also that can explain the nonlinear interaction between independent and dependent variables. So long-term and spatial variation of water quality can be monitored using Landsat and Sentinel and other satellite data. For example, MODIS or VIRUS and other type of satellite, like the Golden series of data from China. So that's all. Thank you.
Thank you so much. There was a beautiful song somebody played, so it's maybe high appreciation to you. Thank you so much, Professor Song. It's very interesting lectures, and we can see that there are a lot of application on this water quality monitoring you have shown us today, which can be done using free dataset that can utilize like Landsat dataset. And also in the closing remarks, you have also showed us there is a potential to replicate all those things to other satellite, even for MODIS and also Geofan satellite data and any other Sentinel data. It's really interesting, and your model on that derived TSM and TSI are very interesting, and you have validated with very high accuracy. And then this research that also shows us, provide us a great insight on this lake water transparency mapping. It's really great because I can see many lakes in our Hindu Kush Himalayan regions are affected by algal bloom and also these transparency things. There are many lakes, no transparency. And because there are many rivers, streams coming from mountain, they depositing a lot of sediments to the lakes, and then the beauty of lake already gone, and there are many fish farmers are migrating to other places. So I think this research really provide insights and also generate curiosity to all the participants here. And today I ask participants to share the question if they have, but I did not see any questions there. I think they will have some questions in the future. If they have any questions in the future, maybe they can come back to you via us, or maybe directly contact to you. Thank you. Thank you so much.
Thank you. Thank you. Yeah. Thank you.
Thank you very much. Thank you. So now, since we have less time, now I wanted to